Thanks for connecting today. My name is Alex David Uraz. I'm the lead seminar organizer for the IAU's working group on active B stars. So welcome to our monthly seminar, and it's my pleasure this month to introduce you to Professor Jim Fuller from Caltech. Dr. Fuller started his career I have my notes here, at Whitman College for his bachelor's degree before doing his graduate studies at Cornell, and has been at Caltech as an assistant professor since 2017. And today he'll be talking about magnetism in stars with radiative envelopes. So please, Jim, without further ado, take it away.
Okay, thanks, Alex, and thanks for inviting me. It's nice to be able to talk about, magnetic fields for a whole talk. A lot of the times they're just, one bullet point at the end of the talk saying that they might be important, but here we're really going to dig into them a bit. So I want to talk about a few different things I've done, trying to understand what magnetic fields look like, not just at the surfaces of stars, but in the interiors of stars. So really building on new types of observations to see what we can learn about magnetic fields inside of stars. And one of the issues here is that actually even just computing a stable equilibrium is pretty tough when you add in magnetic fields. So the first thing that happens is once you have a magnetic field, there's magnetic forces that affect the structure of the star. So it will affect the pressure and density and temperature structure. There have been a number of recent works that have tried to compute what this looks like. But one of the important issues that hasn't really been addressed, or at least much less thoroughly, is the issue that the star needs to not only be in hydrostatic equilibrium, but in thermal equilibrium. So once you change the temperature configuration of the star, you're going to have heat diffusing and changing that. And that's going to be important when you're talking about a long-term equilibrium. And one of the types of data that we have gained a lot of recently is things like luminosity modulation of stars due to stars that are both rotating and magnetic fields. And so the idea is there's some magnetic field in the star, and the magnetic pole is either hot or cold. And as the star rotates around, you see the magnetic pole go in and out of view. And so you'll see periodic luminosity variations at the rotational period of the star. But, I wanted to understand this process. And when I dug into the literature, I realized there was basically no answer for how large of a fluctuation you should get in terms of surface temperature, how that relates to the magnetic field. Even the sign of the response is not clear. Should the magnetic pole be hot or cold? I think none of that was actually very clear, which was surprising. And like I said, we're getting a lot of measurements of stars doing this. So what I'm showing here is just one example. This is a paper by Ilaria Katso here at Caltech. This is a magnetic white dwarf, but we see similar kinds of variations for magnetic A-type or B-type stars, where you see some sort of periodic modulation in their flux. In this case, it's like a few percent in G band, about 1% in R band. And in this case, this is a rapidly rotating white dwarf that rotates at a period of 6 minutes or something, and has a 600 megagauss field. So that's quite extreme for a white dwarf, but it's not actually that different. It's just basically a scaled down version of a magnetic A-type or B-type star. So a lot of the physics that I'm going to talk about, it's really focusing on main sequence stars, but it could apply to many different types of stars. So so the issue is, what do these magnetic spots actually look like? So some naive estimates for what they might look like are things like, you could guess that the magnetic pressure perturbs the gas pressure at the surface. And therefore you might expect temperature perturbations and luminosity perturbations that are kind of order the magnetic pressure divided by the gas pressure. And if you do that calculation for a main sequence star, you would get that even a 1 kilogauss field makes a huge impact on the radiative flux coming out of the surface of a star. The problem with a naive estimate like this is if you have one part of the star that's hotter or cooler, there's immediately going to be heat that diffuses into or out of that region. And so the thermal structure of the star will change on a thermal timescale in response to that. So that's an important issue. Another naive estimate might be like a von Zeipel type estimate, where maybe the luminosity perturbation of the surface of the star goes something like magnetic force divided by gravitational force of the star. And if you plug in numbers for that, you'd get that a 1 kilogauss surface field should produce maybe a few parts per thousand luminosity fluctuation. And that's, I'd say, closer to what we actually observe. But as we'll talk about, again, you have this issue of that kind of estimate is not really valid because we have to compute how heat will diffuse throughout the star. And that's going to really affect what the temperature structure actually is at the surface of the star when it's in equilibrium. So as I said, there has been some prior work on computing these structures, but most of it has basically sidestepped this question of thermal equilibrium. So there's been a lot of recent work by a few authors. One as Duez and Matisse did some very seminal work on this more than a decade ago now, where they computed what the perturbed hydrostatic equilibrium of a star would look like. But they assumed adiabatic perturbation. So they basically assume that the temperature or density perturbation is just directly proportional to the pressure perturbation. And in that case, actually, the system of equations becomes fairly simple to solve. But the problem is, again, that as soon as you have some part of the star that gets compressed and heated up, then the heat is going to diffuse out of that region and you will change the structure. So we really need to solve for the entire problem together. Okay, so how do we actually do this? So I'll walk you through the process that I use, and then we'll talk about some of the caveats. This is not, unfortunately, the final answer, but I think it's a step forward in terms of understanding how to do this. So the first step is we need to make sure our magnetic field is divergence free, right? That's just, it needs to obey Maxwell's equations. And so the way people often do this is they decompose the magnetic field into basically a poloidal and a toroidal flux. So this capital psi here, this is the poloidal magnetic field flux. And if you write the radial field as basically an azimuth or a theta derivative of that, and the theta field as a radial derivative of that, you can plug this into, you can take the divergence of this type of field and you can show it's always equal to 0. I'm going to assume axisymmetric fields. So that means the field has some axis of symmetry. This doesn't have to be the same as the rotational axis of the star. For the calculation I'm doing, I'm not including rotation at all. I'm just calculating the magnetic equilibrium. But there's been lots of work showing that purely poloidal or purely toroidal fields are unstable. So it needs not only a poloidal field, which is the r and theta components here, but it needs a toroidal field, a phi direction of the field. And so there's some function f that basically describes the toroidal magnetic flux. And so a lot of this recent work has shown that the lowest energy state, which we might expect a system to relax into, is one where this toroidal flux f is basically just directly proportional to this poloidal flux psi. And the constant of proportionality, lambda, basically relates the toroidal magnetic field to the poloidal one. So this constant lambda is basically related to the helicity of the magnetic field. The larger it is, the larger your toroidal field and the larger your magnetic helicity. People often talk about helicity in terms of magnetic fields because you can show that that's a property of the field that is basically conserved as it evolves. Dissipative processes can change the helicity, but to first order, it does not change as the magnetic field relaxes into an equilibrium. So it's a quantity we might expect to be conserved and to really be a fundamental property of the magnetic configuration. You can also show that in this simple limit, where the toroidal flux is just directly proportional to the poloidal flux, then the angular structures of the magnetic fields obey certain eigenfunctions. And the one that comes into play, the simplest eigenfunction we can have, is basically just that this poloidal flux goes like sine squared theta. And this is basically a dipole magnetic field. This means the magnetic field is strongest at the pole, weakest at the equator. And so what I'm going to do is decompose this magnetic field into basically some radial function, psi of r, times sine squared of theta. And again, that's basically a dipole field. Of course, real magnetic fields will have more complicated configurations, but I'm just going to just focus on the purely dipole case to just try to understand that case to start with. So when we make this choice, basically all of the other variables in the equations, like the pressure perturbation, the temperature perturbation, all of that stuff also has the same angular dependence. Okay, so what I've done in my work is basically put in these magnetic fields into the equations of hydrostatic equilibrium, and then I'm calculating the new hydrostatic equilibrium of the star. And so I'm basically perturbing things like the density, the pressure, the gravitational field in the star, and I'm solving for a new hydrostatic equilibrium. So with these two equations on top here, these are basically just equations of hydrostatic equilibrium. All these terms involving psi, these are what the magnetic field actually looks like when we decompose it this way. So these are all the Lorentz forces, and all the terms on the right are just the normal pressure force, gravitational force, etc. So the top equation here is the radial, in the radial direction. The bottom equation is in the theta direction. So that's our magnetic equilibrium. And the next thing we have to do is compute a thermal equilibrium. And so what we do is basically just take an energy equation and an equation of radiative flux or radiative heat diffusion, and we perturb those. And so then we can relate basically a perturbed luminosity to perturbed temperature and density, etc. So these other terms here, like this is a perturbed energy generation rate, because that depends on the temperature and density. So we're taking all that into account. This bottom equation is the heat diffusion equation, and so it depends on things like the derivative of the opacity with respect to temperature and density. So these are similar to equations that we solve, say, when we're computing the oscillations of a star. It's just that now we're solving for a zero frequency equilibrium response of the star in response to these magnetic fields. Okay, so we also need some boundary conditions, and it turns out there's quite a bit of subtlety in how we choose this, which is often the case with boundary conditions. So at the inner boundary, at the center of the star, we basically need a bunch of these perturbations to vanish. At the outer boundary, there's a few equations we have. So one is basically, this equation here is essentially a perturbed black body equation. We're requiring the perturbed flux to obey a black body relation. This is a perturbed gravitational potential, which has to have this kind of form. We also have a normalization. Basically, we have to choose some amplitude of the magnetic field. That's what this equation is. And then to solve this system of equations, we actually need one more boundary condition. And how we choose this will end up dictating the response of the star to the magnetic field. So there's going to be a few different choices we can make, which I'll discuss, but that's actually going to have a big impact on what the perturbed star looks like. So let me just show you an example of what the magnetic equilibrium will look like. So this is a plot of, in the meridional plane of the star, the plot of the toroidal field on the left and the poloidal field on the right. So the colors indicate basically the strength of the magnetic field relative to its maximum value. So you can see that the poloidal field is strongest at the center of the star, whereas the toroidal field is actually strongest kind of 2/3 of the way out of the star in this case. And these orange lines, these just show the poloidal magnetic streamlines. So the actual configuration of the star is like a twisted dipole, but the orange lines show basically the untwisted part of the dipole field. So this is similar to magnetic equilibria, not in thermal equilibrium, similar kinds of structures. But now we're actually computing the full response, including that effect. So what we do here is we basically solve the system of differential equations for what the magnetic structure looks like. So now I'm going to show you some examples of different configurations that it could have. So on the right, we're showing profiles of things like this poloidal flux, the perturbed pressure in the star, and the perturbed luminosity. And one of the most important things we're interested in for this problem is, what is the luminosity perturbation at the surface of the star? That's going to tell us actually how these magnetic fields create magnetic spots. And you'll notice that there's a bunch of lines here. Each one of these lines is indexed by beta. And in this case, beta is essentially a parameter determined by that last outer boundary condition. It basically tells us the strength of the magnetic forces inside of the star, because you can actually have magnetic fields with beta equals 0 that actually have no Lorentz forces. That would be some equilibrium magnetic field that exerts no forces on the star, and so the perturbed density, there would be no perturbation to the density and temperature, etc. So that actually is one solution for kind of a general boundary condition, but I'll talk about why those solutions are probably less likely in nature. But you can see that this beta parameter basically just determines the amplitude of the star's response in terms of pressure, or density, or temperature. So you can see small values of beta have really small pressure perturbations, small luminosity perturbations. As we ramp beta up, we get larger and larger perturbations. And you also see that that affects the magnetic structure itself. So higher magnetic forces, you actually need to change what the magnetic field looks like in order to maintain an equilibrium. So as we go to higher magnetic forces, we actually get a field that's more and more centrally concentrated. So it becomes weaker at the surface and stronger in the interior. The other thing we could do is we could keep that value of beta fixed, and we could just vary the helicity. So again, the helicity lambda here is basically just telling us how strong the toroidal field is compared to the poloidal field. And so what you see is that as we go to larger values of lambda, higher helicity, we have a similar effect where we make the magnetic field weaker at the surface and stronger in the interior of the star. But we don't affect, in this case, the pressure and luminosity perturbations by very much. So that's mostly determined by the beta parameter. So how we choose the surface boundary condition is going to be very important. And one of the issues here is that we might expect the magnetic field to kind of smoothly change towards roughly a dipole configuration, a dipole force-free configuration in the atmosphere of the star, right? We don't want magnetic forces in the star's corona because there's basically no gas pressure there to resist those forces. So we expect the magnetic field to have a nearly force-free configuration. And in that case, you need the magnetic field to basically follow a dipole law. And so the magnetic field needs to scale like r to the -3 near the surface of the star. So if you implement that boundary condition, that the magnetic field falls off as r to the -3, then basically, essentially what you're doing is you're fixing the value of beta for a given lambda. And so then we can just calculate what the magnetic equilibrium looks like as a function of lambda. And so in this case, what we see is that higher actually lower helicity in this case, actually makes the magnetic forces stronger. That pushes the magnetic field deeper into the star, so we get a larger magnetic field inside of the star. And we also get larger perturbed pressure and luminosity in that case. So these might be examples of more realistic magnetic configurations in real stars, where we expect them to roughly approach this potential configuration or force-free configuration near the surface. So what actually is the surface luminosity perturbation? Everything I was showing you before is just essentially an eigenfunction that can be scaled up or down with the magnetic field strength. If you actually compute what this luminosity perturbation is, or the fractional luminosity perturbation at the surface of the star is, as a function of the poloidal magnetic field strength at the surface of the star, then you get plots like this. And you can see that for observed magnetic field strength of a kilogauss or a few kilogauss or something, we expect the luminosity perturbations to actually be super tiny, like less than 1 part per million. So basically what this means is realistic magnetic field strengths probably are not enough to actually perturb the internal density and temperature profiles of the star such that we get an observable surface luminosity perturbation. And it depends on things like the magnetic helicity and exactly how you treat this outer boundary condition. So I said, I think the most realistic values are like this green dashed line and this blue dashed line. So that can affect the amplitude by an order of magnitude or something, but we still are getting very large, very small surface luminosity perturbations, or in other words, very small temperature perturbations of the surface of the star. So basically what this means is, if these calculations are close to correct, it means that the observed luminosity perturbations we see in magnetic stars cannot be explained by this process, by the magnetic field actually perturbing the internal structure and therefore the outgoing luminosity of the star. Instead, what I think is more likely is that the magnetic field is actually affecting things like the outgoing spectrum at the surface of the star. Magnetic fields can affect things like the opacity and the outgoing flux of the star. It can affect the spectra. It can affect the actual, the line profiles and line shapes and all that. So I think it's more likely that actually the spectrum of the star is changed by the magnetic field. Not so much the bolometric flux, but just the spectrum or the amount of flux in a given band might be altered by the magnetic field. And that's probably more likely to account for the photometric variability that we actually see in magnetic stars. So even if magnetic fields can't explain, or at least these calculations can't explain luminosity perturbations from stars, we can still learn something about what magnetic structures, realistic magnetic structures look like inside of stars. So what these plots are showing is the radial and theta and phi component of the magnetic field as a function of radius within the star for different helicities and different magnetic field strengths. And so what we see is that if we go to larger helicities or larger magnetic forces, then basically the black and purple lines become larger at the center of the star. So this value here in the bottom panel, what this means is that the surface magnetic field strength is 30 times weaker than the central magnetic field strength. So that's really important, right? We want to be able to try to estimate what the core magnetic field strengths are for a given surface magnetic field strength. So in this case, if we saw a magnetic field at the surface that was something like a kilogauss, we'd expect the central magnetic field strengths to be of order, 20 or 30 kilogauss or something like that. So rough estimate for core magnetic field strengths are maybe an order of magnitude larger than the surface magnetic field strengths. So that's quite different from a simple dipole configuration, where the magnetic field goes like 1 over r cubed everywhere. that kind of behavior we only get near the surface of the star, and in the core we of course have to change the structure. So we think maybe an order of magnitude larger central field strength. So there's still some issues in exactly how to do this calculation. So one of the issues is that in the star's corona, we expect probably not only the magnetic forces are close to zero, but also probably the current associated with the magnetic field should be pretty close to zero. Because if there's current flowing around in the corona, that could cause a lot of dissipation, because things like electrical resistivity or magnetic diffusivity become more important near the surface of the star. So if you want the current to vanish at the surface of the star, remember the current is basically just the curl of the magnetic field. You can show within this formulation that I've used that the current goes proportional to this helicity lambda, and then it's proportional to basically the magnetic field strength in terms of the poloidal components. So if we want this current to vanish, we either need the helicity to be zero, but we know that's unphysical because we know those kinds of magnetic fields are unstable. Or we need the radial or theta component of the magnetic field to go to zero at the surface. But that's also unphysical because we see stars with radial and theta components of their magnetic fields. So probably what this means is that there's a breakdown in our assumptions near the surface of the star. In particular, we assumed that this toroidal magnetic field was just directly proportional to this poloidal flux. And that's kind of a lowest energy state, but that's probably not the state that you actually reach in a real star where there's dissipative processes changing the magnetic field near the surface. So probably what happens is this magnetic field doesn't just have a sine squared profile at the surface, and probably the way the toroidal and poloidal field are related to each other is a little different from our assumptions. So in that case, you'd have some sort of non-separable radial and angular dependence of your magnetic field geometry, and that makes the calculation much harder, especially when you're accounting for all these thermal diffusion effects and things. So I think that's a direction for future work, is to try to calculate that kind of structure, a structure where the currents go to zero at the surface of the star, but where you also have, a non-zero magnetic field at the surface of the star. Those are the kinds of structures we need to compute in future work to really nail down what these magnetic fields look like. So all the results I showed you, I guess I forgot to mention, those were for a 3 solar mass main sequence star. But I think what we've learned is that we know roughly how the magnetic field scales, and so we can scale this to other types of stars. So in our calculations, the luminosity perturbation at the surface of the star goes like the magnetic field strength squared. It basically goes like magnetic energy density divided by gravitational energy density. It scales that way, although it's probably larger than that by this factor beta. And the most plausible values of beta that we found in our work were betas of like maybe of order 100 or 1,000 or something. So it's probably kind of 100 times larger than just magnetic energy divided by gravitational energy. But that still is a very small luminosity perturbation. So if we put in appropriate values for massive stars, we'd still get very small luminosity perturbations for them. And I don't expect anything about the physics to greatly change for magnetic stars. For massive stars. So again, I think probably the magnetic fields are not perturbing their luminosity profiles very much. It's probably more like their spectra are being perturbed, and maybe that accounts for photometric variability we see from them. Now in white dwarfs, again, these are radiative stars where this calculation will work pretty well. There's a different effect that might be important in white dwarfs, which is this effect of anisotropic conduction. So what happens there is electrons that are degenerate, which actually carry heat in white dwarfs. Degenerate electrons have long mean-free paths, but they should also basically be forced to move along magnetic field lines. So that means you can have anisotropic conduction, where you transport heat more efficiently along magnetic field lines than perpendicular to magnetic field lines. And that effect may actually be quite important for white dwarfs. And so that's something I'd like to look at in the future. I'd be surprised if we'd get a hugely different result for white dwarfs in terms of scaling this equation up here, but it might be that we get a larger effect. So that's something I'd like to look into. Okay, so I want to actually pause there because that's kind of the end of this magnetic equilibrium magnetic field part of the talk, and see if there's any questions on this part of the talk.
Okay, so if you have questions, maybe just raise your hand on Zoom. Jim, I might have a question, and maybe this is kind of previewing some of what you're going to be talking about. So if I'm a little out of line, let me know. But it seems to me that your magnetic models, you're basically predicting the magnetic structure throughout the entire star. So have you looked at how that structure impacts angular momentum transport? And if so, do you have any sort of testable prediction coming out of that?
Yeah, so I can talk about angular momentum transport next. For these kinds of stars that are threaded by pretty strong magnetic fields, I'd expect them to keep the star essentially rigidly rotating. So I can talk about magnetic angular momentum transport in the case of weaker magnetic fields that actually get wrapped up by differential rotation. But in these kinds of stars with strong magnetic fields threading their radiative zones, I'd expect pretty much rigid rotation, just because the magnetic coupling time is quite short if you have a strong magnetic field like that.
Great, thanks. Any other questions before you move on? Okay, I'm not seeing any hands up.
So
I guess.
Actually, I want to ask you all, so next I was going to talk about how we can detect magnetic fields with asteroseismology, but I could talk about how magnetic fields affect angular momentum transport. I think I'll probably only have time for one of those things. Does anybody have a vote?
So I guess we have at least one response in the chat saying angular momentum transport. I don't know if anyone else wants to. Oh, okay. Someone else concurs.
Okay. All right. Well, I'll jump to that part of the talk then. So the summary of the asteroseismology part is that we can measure magnetic fields. We can actually detect strong magnetic fields in the cores of red giant stars with asteroseismology. So we think a lot of red giant stars have kind of 10 to the 5 Gauss magnetic fields in their cores. Now, the other thing that we can do with asteroseismology is measure spin rates of the central part of the star. And that's really important for understanding angular momentum transport, because typically as stars evolve, their cores contract, their envelopes expand. And so if each part of the star conserves its angular momentum, you'd expect the core to start rotating much faster than the surface. And with asteroseismology, we can actually measure rotation rates of different parts of the star simultaneously. So this is an example of the splitting of a dipole oscillation modes in a red giant star, where we see this particular oscillation mode is split by rotation, and this particular oscillation mode is split by rotation, but it has a wider splitting. And the reason is this star lives in the core of the star where the rotation is faster, and this mode lives in the surface layers of the star where the rotation is slower. So we can actually get some constraint on different parts of the star. And mostly I'm going to talk about observations in red giant stars. And in that case, the oscillations that we see, they have this acoustic mode character in the envelope, and they propagate through the core as gravity waves. And actually, it turns out that's what the part of the star that these modes are most sensitive to. So we actually get better measurements of their core rotation rates than their surface rotation rates. So there's been quite a bit of work on this over the last decade. Here's a nice plot from one of Benoit Mosser's paper, showing measurements of the core rotation periods of red giant branch stars. There are many more now that are kind of similar. There's a big scatter here, but they're kind of typically of order 10 or 20 days for stars. These are mostly 1 to 2 solar mass stars going up the red giant branch. And if you look at them later when they're burning helium in the cores, when they're on the red clump, the cores are even slower. Their periods are something like 100 days. So to put this into context, this is very different from what pretty much any models had predicted. So what's shown here are measurements. These are the same measurements I was showing before of these core rotation periods as a function of the radius of the star. So stars move from left to right as they go up the red giant branch. And what you can see is that the observations fall neatly between all of the different models here. So the black line is basically a model where the star remains rigidly rotating. The green lines or purple lines are models with only hydrodynamic angular momentum transport mechanisms, and those are, the star essentially conserves its angular momentum, each shell of the star in those models. And so those models predict the core to be rotating 100 or 1,000 times faster than observed. So that's clearly not happening. The red line is a model incorporating the Tayler-Spruit dynamo into one of these models. And you can see that does a better job, but it's still getting the core rotation rate. It's predicting that it's about 10 times faster than what's actually observed. So this suggests that it suggests that angular momentum transport is stronger than any of these models predict. And I think that there's a good chance this is due to magnetic torques within the star. So the work I've done is kind of reinvestigating this Tayler-Spruit dynamo. And the idea here is that now we're imagining that we start with a really weak magnetic field. And a really weak magnetic field will just, if there's differential rotation in the star, it will get wound up. You know, it's like winding up a string by twisting it. So it just gets wound up. And eventually you form these toroidal field loops that become unstable. Like I said, a purely toroidal field is unstable. And that's basically what starts happening here is your toroidal field is much stronger than the poloidal field, and it becomes unstable, and you get these field loops slipping sideways. And that's called the Taylor instability. And the important thing to note about that is as soon as these field lines are slipping sideways, we're basically producing radial displacements of the fluid, and therefore we're going to produce a radial component of the magnetic field due to this instability. And so that means we can potentially have a dynamo. It's like an alpha omega dynamo where the differential rotation is creating the toroidal field, and then this Taylor instability is causing perturbations that might be able to regenerate the poloidal field. And once we have both a toroidal and a poloidal magnetic field, we have Lorentz force that transports angular momentum. And so that's the idea behind the Tayler-Spruit dynamo. Now, the important thing I want to highlight here is that the outcome of this instability is not well understood, right? This is a linear instability, but the nonlinear outcome we don't understand very well. So the Tayler-Spruit dynamo is basically it's a closure model for this instability that predicts how large this instability grows and then how strong of a toroidal and poloidal magnetic field we have at the end of that instability. And that gives you an effective viscosity or effective angular momentum transport given by this equation here. And the way this scales is it scales like the rotation rate of the star, omega, divided by the Brunt-Väisälä frequency. That basically tells us the strength of the buoyancy forces that are resisting radial motions. And in this prescription, it scales like that ratio to the 4th power. And that's important because this ratio of omega to n in red giant stars is like 10 to the minus 3 or 10 to the minus 4. It's a very small number. And that's raised to a large power, so we get not very much angular momentum transport. In the work I've done, I've made some arguments that the instability should actually be able to grow to larger amplitudes. And the reason for that is that the rate at which energy is dissipated by this instability should be less than predicted by Spruit, because we can't actually dissipate the entire magnetic field. We can basically only dissipate the kind of non-ordered component of the magnetic field that we get due to this instability. So the consequence of that, and I can go into details maybe afterwards if people are interested, but the consequences are we get less dissipation, and so the instability can grow to larger amplitudes, so we get a larger poloidal and toroidal magnetic fields, and so we get more angular momentum transport. And in this model, it scales like that ratio of omega to n to the 2nd power, it turns out. So that gives us quite a bit more angular momentum transport. So we can put this model in, for angular momentum transport into a star and compare it with the data. And that's what I'm showing here. Again, these ovals are kind of asteroseismic measurements of typical red giant core rotation rates. Again, those are like 10 or 20 days. Core rotation rates during the helium burning phase, that's this green oval, those are about 100 days. We also have some nice white dwarf rotation rate measurements, and white dwarfs typically rotate at periods of a day or two. And so what you can see is these models. So the black line is this Tayler-Spruit dynamo, just the classic dynamo model. And like I said before, that overpredicts the rotation rate by a factor of 10 or 20 or so. The red line is this new model. And you can see that it actually matches the data quite well. It's not perfect, but it gets much closer than basically any of the other prescriptions. There is this fudge factor alpha in here. This is an order unity coefficient that we expect, we expect this to be of order unity because all the arguments that lead to these kinds of equations are kind of order of magnitude twiddle arguments, and there's probably factors of 2 and pi and stuff that aren't accounted for. So the best way to actually calibrate these kinds of models is with some factor alpha, which we expect to be of order unity. And that's exactly what we need to match the data in this case. So that's somewhat reassuring. I think I'll skip over some of this. I want to also say some of the implications for massive stars. So most of the data we have, like all this data, this is for low mass stars, right? These are like 1 or 2 solar mass stars or white dwarfs that are coming from those kinds of stars. In massive stars, we can't actually use asteroseismology to directly measure the core rotation rates. What we can do is measure rotation rates of young pulsars and compare model predictions to those kinds of rotation rates. And so that's what's shown in this plot. This is basically putting in the same model into massive stars. We have a 10 solar mass model and then going all the way up to a 40 solar mass model here. And what's shown in this plot is the specific angular momentum contained in the inner core of the star, which will end up becoming a neutron star. And what you can see is it starts at a high value, but as the star evolves, it loses over 99% of its angular momentum. And most of that angular momentum is lost right here. This is the end of the main sequence. So what's happening here is the star runs out of hydrogen and its helium core contracts by a large factor before it starts helium burning. And so during that phase, it's trying to contract and spin up, but we have these magnetic torques via this modified Tayler-Spruit dynamo that are extracting most of the angular momentum and preventing that spin up. And so in these models, the angular momentum at the end is quite low. And if you then just assume that's conserved all the way to the neutron star after core collapse, which is a big assumption, probably the core collapse process actually alters it a bit. But the predicted neutron star rotation rates are kind of the order of 100 milliseconds or a couple hundred milliseconds for these types of models. And that's actually pretty consistent with typical estimates for newborn pulsars. Some of them are fast, like the Crab pulsar was born at 20 milliseconds or so, but that's actually much faster than the average pulsar, which is probably closer to 100 milliseconds. So to first order, these predictions are actually fairly consistent with young pulsar rotation rate measurements. So again, it's interesting that these models can roughly reproduce both white dwarfs and pulsar rotation rates. So the other question then that naturally arises is, well, what about black holes? So again, we can put the same model into black hole progenitor models. And this is showing the angular momentum content contained within the helium core of massive star models. And that's the part of the star that we definitely expect to fall into a black hole if the star forms a black hole at the end of its life. And again, these kind of cliffs in angular momentum, the stars evolve from left to right. And where the angular momentum in the core plummets is at the end of that main sequence. And in this case, the stars are losing more than close to 99% of their angular momentum as they evolve. So similar to the neutron star case. So they typically wind up with small amounts of angular momentum. And you can equate that to a black hole spin. And that's what's shown in this plot is the black hole spin that you'd get as a function of the mass of the star. And all these black dots here, these are models of single stars. Basically, you can see that the predicted spins are very small. They're less than 0.1. So these models predict very slow black hole spins. There are some exceptions, which I won't go into in too much detail, but this green and yellow model, these are basically binary models. One is a model where the star gets tidally spun up during the helium burning phase. And so that basically rejuvenates the angular momentum of the star. And so in that case, you actually can form a pretty rapidly spinning black hole upon core collapse. The yellow model is a model of what's called homogeneous evolution, where basically the whole star gets burned into helium. And in that case, what happens is there's no expanding hydrogen envelope to suck up all the angular momentum from the core. Just everything is the core. And so the core conserves its angular momentum. And so it can produce a rapidly spinning black hole when it collapses. So if those processes happen, we can get pretty high spin black holes, but otherwise these models predict pretty low spin black holes. And that is, again, to first order consistent with what we're seeing with measurements from LIGO, which is that most of the merging black holes appear to have pretty low spin. And there's been a huge amount of work on this in the last few years, trying to analyze the data to figure out what the individual spins of the black holes are. Basically, that's extremely difficult. What you actually measure is chi-f, which is like a projected spin of both black holes into onto the orbital axis. And the uncertainties are large, but basically, I think everybody agrees that because these are clustered around 0, most black holes have fairly low spin. And there are a few at higher chi-f that probably have higher spin. Now, there's still some controversy about exactly how slow the spins of these things are. Are they less than 0.2 or are they less than 0.03 or whatever is not clear because the measurement uncertainties are large. But they are fairly small, and that is what's predicted by these magnetic angular momentum transport models. So we need to do a lot more work to understand both the data and really understand the theory of this angular momentum transport, because I think there's still a lot of uncertainty there. But we are getting this picture of, in general, most of the angular momentum seems to be extracted out of stellar cores before they form compact objects. So that's why we tend to get fairly slowly rotating white dwarfs and neutron stars and black holes. Okay, so we have about 10 minutes left, so I think I'll pause again and ask if there's more questions.
All right, anyone, you can just raise your hand, or actually there's not that many of us, so you can just also unmute yourself and ask your question.
Yes, I would like
Yes, please go ahead.
Yes, so Jimmy, you showed that in some of the models, most of the angular momentum is extracted after the main sequence, right? But there are asteroseismic measurements from subgiants, and you may be aware that the Tayler-Spruit dynamo cannot reproduce very well the rotation rate of the subgiants, and actually the transport is over-predicted in those cases. So I would like to know what is your feeling about the theory. Is there anything that could be changed to bring the models into agreement, or what is your feeling about that?
Yeah, thank you for bringing that up. So this is a bit of an old plot, and yes, I think you know this issue well, that there's also some measurements of core rotation rates for subgiants, which on this plot would be kind of about here. And the subgiants that have been measured, their rotation periods are a little bit faster than what these models predict. So I think there are rotation periods of like several days in the cores of those stars. So they lie below this red line. There's only like 6 of those or something that have been measured, but they do appear to be systematically faster than what these models predict. So a model that would match all the data would actually kind of go like this. It would go down here, and then it would have to come back up to the red giants. So this model does struggle to reproduce the subgiant rotation rates. And I'm not sure how to simultaneously explain everything. But one possibility is that actually this Tayler-Spruit dynamo is weaker, or this modification to the Tayler-Spruit dynamo needs to actually have slightly lower magnetic torques, and that could be done with like a smaller value of alpha in this equation. But then you'd need something else to also reproduce what we see later on. So if I just showed you one of these models with a smaller value of alpha, it could match the subgiants down here, but then it would also miss all the red giants and clumps and white dwarfs. So I think we don't have a full picture yet, and that's is concerning when we try to extrapolate this to other types of stars, right? Because we think that there's probably a missing ingredient here. But it does get closer than pretty much any other model, any physical model that I'm aware of. There is another interesting model that's been developed by Chris Thompson and Yevgeny Kissin, which assumes that basically the radiative part of the star is rigidly rotating and that there's a lot of differential rotation in the convective envelopes. And I do think that's an interesting possibility, and you can actually get close to explaining some of these measurements that way as well. Although actually I've looked into that. That model also really struggles to explain the subgiant rotation rates. So I don't think that there's a complete picture yet, but it might involve a different mechanism that hasn't been discussed or some combination of those mechanisms. I'm not sure.
Okay, if I may ask other questions. So for massive stars, we don't have many asteroseismic measurements of the rotation rate of the core. So, well, in principle, we could assume anything for the transport, right? But in your opinion, what would be like the critical test to either validate or reject this model with internal magnetic fields?
Yeah. So one possibility that people are starting to look at is like internal rotation rates of B stars, slowly pulsing B stars or beta Cepheid stars. They aren't ideal because they're still on the main sequence, but we do expect the cores to contract somewhat during the main sequence and the envelopes to expand a bit. So if we can measure the rotation profiles of those stars pretty well, we can get a better sense of how much angular momentum transport is going on in the main sequence. And these types of magnetic models predict nearly rigid rotation on the main sequence. It turns out there's actually an exception for very slowly rotating stars. And the reason is that all these torques are predicted to scale with rotation rate cubed. So actually in slowly rotating stars, you can actually get extremely weak torques and you actually can get some differential rotation according to these models. And that has been observed in some very slowly rotating Gamma Doradus and SPB stars. But I think we really need more measurements for kind of stars rotating at ordinary rotation periods of like a day or a couple days. Massive SPB or beta Cepheid stars could be a good test of some of these models if we can get core rotation rate measurements and surface rotation rate measurements.
Thank you.
All right. Any other questions for Jim? So maybe a naive question, Jim, but since we're on this slide, so obviously the model that's shown here is for single evolution, but is the scatter that you're seeing in the observations basically what you would expect from binary evolution, or?
So I don't think so, because most of those measurements are for stars that look single. It doesn't look like they've had any binary interactions. And these are low mass stars, so most of them don't undergo binary interactions on the main sequence. Or lower red giant branch. So I don't think we can appeal to binarity to explain that scatter. Actually, that scatter is a big problem for these kinds of mechanisms, because basically what these mechanisms predict is you sort of, no matter what your initial rotation rate, you actually end up falling kind of right on this red line during the post-main sequence. And the reason is you get stronger torques for rapid rotation. And so all the models tend to converge onto a single line in the post-main sequence, which is different from the observations where we actually see a lot of scatter. And so it's actually hard to explain that scatter with any of the existing prescriptions that I'm aware of. So that's another outstanding issue. Now, again, these are magnetic dynamo processes, so there's probably actually a lot of scatter inherent to the dynamo, right? Anybody who studies magnetic fields knows that they vary in time, and magnetic dynamos are messy, and stars do all kinds of stuff. And so there's a lot of scatter in magnetic field strengths and activity, et cetera. So probably some of that happens for these types of dynamos too, and that might help explain some of the scatter, but that's a piece of the puzzle that we really don't understand at all.
Great, thanks. So I guess we're kind of closing in on the hour here. Maybe there's time for one last question if anyone has any. Okay, then in that case, thank you very much, Jim. I guess I'll applaud on behalf of everyone, or if you want to show your appreciation in the chat. This was a really great talk. So thanks a lot for coming and talking to us about these stars and the magnetic fields. And just a quick announcement. So we will be having one last monthly seminar before the summer break next month. Our speaker will be Young Shao, and he will be talking to us about population studies of B stars, I believe. So stay posted in terms of any updates on this talk. The date and time will be announced fairly soon. So thanks everyone for connecting. Thanks, Jim, for this great talk, and I hope to see you all soon.
Thanks, everybody.